We are now going to define a new mathematical object called a free vector. And a free vector is defined by its length and its direction. Normally we would denote a free vector with a lowercase and a bold, so a bold lowercase letter. But since I'm drawing this, I'll just do a lowercase and underline it. In textbooks you'd normally see it in bold, but this would be very long for me to try to bold out each letter. So if we recap, a bound vector AB has length, direction, and a starting point A. A free vector essentially doesn't have a notion of where it is in free space. So if I draw that as the free vector K, this is a free vector because it has a certain length and it has a certain direction. Then if I draw another vector T, which is parallel to K and has the same length as K, these are meant to have the same length, then T is equal to K. This is because T has the same length as K and it has the same direction as K. Note that we don't care about the starting point. If this was a bound vector, there would be two different bound vectors since they have two different starting points. Now, bound vectors can represent free vectors. So if I draw the bound vector AB, and if I draw the free vector K, this bound vector is in the same direction as K, it has the same length as K, and so we can say that AB represents K. Normally I wouldn't write out the free vector like this. Normally in textbooks you'd see AB as the bound vector and K to show that AB represents the free vector K. And let's just quickly go on to the zero vector. Now when I defined the bound vector, I said that it's defined by length, direction, and its starting point. However, there is a bound vector which does not have a defined direction, and this is the zero vector. Actually, we'll go on to that in the next one.